Good afternoon, everyone. Thank you for joining us in our lunch and learn. I'm just letting people in at the moment, and then we'll start our session. Just to let you know as well, just a few housekeeping notes. This session will be recorded and it'll be available in our social media and our YouTube channel. Also, please ensure that your microphone is all muted just to minimize any background noise. That would be great. And if you have any questions, please save it for later on. We'll have a question and answer session at the end. Or you can pop it on the chat as well. That will be great. If you're not following our social media, please do follow our social media. We do lots of updates, upcoming events, and any like opportunities. I'll put it in the chat. And the link for Symphonia as well is on the chat if you want to find out more about Symphonia. So, our topic for today is large language models can accelerate evidence-based policymaking. This is going to presented by Professor Mark Williams. So I will hand in to you, Professor Mark.
Oh, thanks, Divine. Thanks so much for organising this, and thanks so much everybody who's turned up to hear about how large language models can accelerate evidence-based policy making. So my role is really to be part of a large sort of a team, and my role within that team is to sort of swan around, basking in the reflected glory of all the hard work that everybody else is doing. So I'm very, very privileged to be wandering around, basking in the reflected glory of a whole bunch of brilliant individuals who are doing all kinds of great work. So today we're going to be hearing particularly about the work undertaken by the Symphonia team. So that's Rory Williams, Andrea Samuel, sort of Dan, sort of Burks, who have all done fantastic work on building a platform that allows us to harness the power of large language models in order that we can accelerate evidence-based policy making. But sort of sat behind this. Oh,
Sorry,
I
I think
think
I'm muting Mark. Sorry.
you muted me, Divine. So
I'm
I'm being
sorry.
censored already. And I understand why, because I was just about to sort of say about sort of a Dr. sort of Chris Brown, so I could see your sort of finger going sort of straight on the mute button. Right. So yeah, so the work that we're going to be talking about today was specifically done by Rory, Andrea, Samuel, and Dan, but sat behind Rory, Andrea, Samuel, and Dan is the fantastic ARC collaboration, which is an army of 1,000. But I specifically want to say a massive thank you to Chris, Lydia, and Divine for all the great work that they've done to support the Symphonia team to get the large language model up and running and ready for use. So big thank you to everybody on this sort of slide for all the hard work that they've been doing. But my job today is, as I say, just to take the reflected sort of a glory and just talk to you about the great work that they've done to create this platform. So what we're going to do today is look at the universe's most important equation ever. So you're going to see an equation, which is the most important equation that's ever been invented. We're also going to learn about some different games. So I'm going to talk about 3 different games, and I'm going to give you some top tips on how to play those sort of games. And also, in amongst all of this, we'll learn a little bit more about this Symphonia platform, this new approach to evidence-based policy making. So this is the running order. So I'll start off by just describing the problem. We'll talk a little bit about information theory. So that's the underpinning scientific foundations for the Symphonia platform. Then we'll talk about a specific game called Wordle. We'll touch a little bit on human intelligence and compare and contrast that with artificial intelligence. And then we'll get to the meat of the matter, which is the Symphonia platform and how we hope that it's going to revolutionize policy making throughout the UK and in fact throughout the world and in fact throughout the known universe. So let's start off with our problem statement then. So for a number of years now, we've been trying to address a homework question that was set to us by government. And this was the homework question, and it was set to us, first of all, during the pandemic. And it was set to us because people throughout the UK looked enviously at the work happening in Bradford and the incredible data assets that we're privileged and blessed to have within the district. And that's the connected data, connected routine sort of data, first created through Bourne and Bradford, and then the power of those linked routine administrative data leading to the creation of Connected Bradford, which is now leading to Connected sort of for West Yorkshire, and so on and so forth. And these connected data sets really seem to have great potential to allow us to identify needs, particularly in children and young people, much before we hit a crisis threshold. So this really aligns with government's desire to shift towards more preventative work rather than wait until a crisis unfolds. So the homework question that we were set by government was, how can we use the evidence and data we have to identify risks to children's care, health and education and predict vulnerabilities in the system? And the second part of the homework question was, can we do more to improve local capacity and capability to collect and use data, to understand local areas and properly monitor the risks? So this was a question that was posed many years ago. And over the last few years, we've been working really, really hard to try and get some answers to those questions. And the journey to answer those sort of questions is now, I believe, approaching its end stage. And on February the 23rd, we brought together a fantastic community of data scientists, academics, together with policymakers to start really bottoming out the answers to these questions. So on February the 23rd, a large community, close to 100 people, came together in Manchester to start answering that homework question. How can we use these big connected data sets to identify needs earlier and intervene when we know it's more effective and less expensive? So everybody sat in a room together, and it was clear that there was consensus being developed within that room. And within that room, we were really starting to identify some very solid recommendations that we could give back to government. But of course, what we want to do is make sure that when we give our recommendations to government, they really do reflect a consensus position. This really does have the best possible evidence sat behind it. It really is the expert opinion. Now, we have methodologies that help us establish a consensus, that help us ensure that a position we take reflects all of the available evidence. And we call those processes Delphi processes. So what we wanted to do was really capture all of the learning that was being generated from over the previous years and then distilled on February 23rd in Manchester so that we could give the best possible advice to government. And what government then really wanted us to do is produce a report that lays out for them how they can use big connected data sets throughout the UK to identify needs early and build a country that works for all children and young people. And what they wanted us to do is produce another Child of the North report through our Yorkshire and Humber arc to bring our communities together and tell them what is the consensus position on what they need to do to use data more effectively to ensure that every child and young person has a very possible start in life. So that was the task that they gave us. But the problem is that these reports are really, really difficult to produce. And let's just have a look at why that is. The reason that these reports are really, really hard to produce is because what we are doing is going to our experts and we're asking our experts for their opinion. We're asking our experts to give us all of the evidence that supports their opinion. And then we're trying to synthesize all of that information together. And that synthesis effectively tends to fall on the shoulders of one or two individuals. So you have one or two people who really have got to try and pull all of that evidence together and create a synthesized version of that expert opinion in order that policymakers can act upon the best possible evidence. Now, that's the bare minimum of what we want to do. And that's what we did in the Child of the North reports. And Megan Wood and myself did a heck of a lot of very, very hard work in trying to synthesize all of the incoming information and produce the very best possible reports. But what would be even more powerful is to run that Delphi process, where we bring together that expert opinion, but we also identify where there are differences of opinion or where people seem to be weighting different things in a different way. And this is where the Delphi consensus methodology is very powerful, because what we can do is run an initial round where everybody independently gives their opinion. We can then synthesize all those different opinions. And then we can go back to the group with the synthesized viewpoint and ask them to reevaluate their position, bring any additional information into the equation, and produce a new set of recommendations. So we now have doubled the amount of work that's required. So I said there was a huge amount of work in the first place, just synthesizing all the information. But now what we're doing is now sending that information back out to all those experts and asking those experts to yet again feed into a process, which yet again means that one or two people have got to take all of that input and produce a synthesized output. And actually, if you really want to do a Delphi methodology effectively, you should do that 3 times. So what we see is that there are these big bottlenecks in the process. And those bottlenecks just become more and more problematic the more and more experts that you bring into the process. And that's a problem, because what we really want is a diversity of opinion. We really want to make sure that the expertise throughout the UK is being brought to bear when we're making recommendations to government. And the reality right now is government tend to rely on a very small, select number of experts, typically within the Golden Triangle. And that means that we don't get that wider perspective. It often means that the voice from Scotland or Wales or the north of England is marginalised. And that's deeply problematic when you're trying to create national policies. So the question is, how do we overcome this sort of a problem? And this problem is actually very well known within computing. And it's the problem of a bottleneck. And what you can do within computing is you can build more and more processors into the sort of a system. And something called Armdale's law allows us to actually look at the savings that are accrued if we just bring more and more sort of processes into the sort of a system. And what we know from computing is that adding additional processors speeds up the whole process, so we can get around those bottlenecks. So that's great for a computer system, but what do we do when we're dealing with humans and a Delphi process? The problem is that we can't just add more and more humans to try and get around that bottleneck, because ultimately we need an individual, a couple of individuals taking responsibility for pulling that information together. So simple parallelization isn't an effective strategy when it comes to traditional Delphi methods. And that's the problem that we're facing. So what I want to do now is sort of think, how can we use technology to start overcoming that problem? So what we're now going to do is just consider information theory, because information theory is the scientific foundation of the Symphonia platform that we've developed. And I just wanted to establish a sort of certain sort of a set of philosophical rules that sort of underpin our approach to this problem. So the axioms that I'm going to sort of lay out here are, first of all, that the universe is knowable, right? We all believe that we have some ability to understand the universe, understand the world in which we live. If that weren't the sort of a case, then we wouldn't sort of survive, and we wouldn't be able to build up a body of sort of a knowledge. So we're good at understanding the universe, knowing about the sort of universe. And the state of the universe is described by information. And we can use that information to make predictions, decode hidden sort of variables, and extract meaning. And we can do that using inference techniques. So inference uses probability to extract meaning, make predictions, and decode hidden variables from information. And inference is absolutely central to human function. If we didn't make inferences, then we wouldn't survive as a species. In fact, inference is central to science. Everything that we do within science is to allow us to make predictions about what we'll see under certain conditions. So without inference, there is no science. So it's the case that inference provides humans with the only source of information about the universe. So if you think about all of your brain cells, All of your brain cells are within your skull. Those brain cells, barring some catastrophic incident, will never be exposed to the external world. They'll never be exposed to the universe. And yet, through inference, through processing information, storing information, using that information to test hypotheses by acting upon the world and changing the state of the world, you can learn about the world. We can learn about the universe. And I say that's the foundations of what it is to be human, and it's the foundations of science. So inference is absolutely central to everything that it is to be human. It's central to everything about science. And it follows that that inference is based upon information. And I've defined information in the following way. So information is the state of the universe relative to an observer measured as the logarithm of the number of its possible states. And so the equation on this slide is the most important equation, arguably, that has ever been developed by humans. And this is the equation that really underpins all of the information revolution. It underpins everything that we mean when we talk about artificial intelligence. So this is Shannon's equation. And this equation was the first step towards understanding that information really reflects the physical properties of the universe. And what this equation tells us is that information is related to the likelihood of a particular event. So the greater the number of possible events, the greater the information content. And what this means is the more unlikely event, the more information is contained within that event, so that less probable events have higher surprisal. So let me just give you a concrete example of that. So if we just think about tossing a coin, there are two possible events that will come out of that action. So the coin, let's not be pedantic and get the coins that are landing on its sort of edge. The coin's either going to land heads up or tails up. So there are two possible states. And so what that means is that after we toss the coin and we find out which way it's up, we've obtained some information about the new state of the universe. And we can quantify that using the sort of Shannon equation. And we can find out that learning the outcome of a coin toss, learning about the state of the universe after we toss that coin, gives us one bit of information. But if we think about rolling a dice, well, there are 6 possible outcomes to that sort of a dice. So that means the state of the universe, after we've rolled the sort of a dice, gives us more information. We can end up with 2.54 bits of information once we know the outcome of a dice roll. So we can see that information is related to the likelihood of an event. So now let's sort of think about a different part of the universe. Let's just think about the number of letters in the English language. And let's think about a book. Let's call it Alice in Wonderland. And we can just think about the number of letters that are contained within that book. And we can think about the relative frequency that we'll see those letters appear within that sort of a book. And this plot here shows you graphically the relative frequency of the individual letters that appear in Alice in Wonderland. So we can see that A appears frequently and J appears infrequently. So if you randomly selected a letter within Alice in Wonderland, then it's far more likely to be an A than a J. And if you see the A, you're going to obtain less information than if you find the J. And what we can actually imagine is actually making little plastic tiles with all of the letters on it, and then putting those letters in a bag, but making sure the number of tiles correspond to the relative frequency of the letters. So we can imagine a bag containing all these little tiles where the number of tiles reflects the frequency. And then we can imagine putting our hand into that bag and pulling out a letter. And of course, the information that we obtain will be a function of the relative frequency of how often that letter appears within the book. So some letters will give us more surprise, will have a higher surprisal level than other letters. And we can actually quantify the level of surprisal using Shannon's equation. So on the right-hand side of this slide, you can see the relative amount of information that is associated with each letter as determined from the frequency of those letters within Alice in Wonderland. And some of you are probably familiar with the game of Scrabble, and you'll be familiar with the idea that Scrabble has certain values associated with certain letters. So if you're not familiar with the game of Scrabble, you randomly select some of these different tiles from a bag like the one I've just described, and your task is to make words using those letters. And if you select less frequent letters, then you score higher points because it's hard to make words out of those letters because they occur less frequently. So we can actually calculate, as I say, the information content for each one of those different tiles, each one of those Scrabble sort of letters. And as I say, the information sort of content is given on the right hand of this screen. And I had a fun night in London last night. It was pretty wild when I actually decided to try and sort of map between the values which are given to the Scrabble tiles and the actual information content. And I kind of realized there's some kind of rule that's a little bit like the sort of following, where clearly whoever designed the games decided that less than sort of 5 bits of information corresponded to 1 point on the Scrabble tile. If it was between 5 bits and 5.2, then you'd get 2. If it was between 5.8 and 5.2, you get 3 points, and so on and so forth. Um, and I thought that was quite interesting because what that actually showed me was that some of those letters, so it works really quite well for most of the letters, but for a small number of letters, it doesn't work so well. So if you've got a letter B, G, J, or V, you actually really are dealing with letters that are problematic because they have less points than they should get. However, if you get an H, then you're actually getting more points than you should have. So that perhaps gives you some top tips as to how you should get rid of your letters whenever you're playing Scrabble. So this talk has some practical implications for your everyday life as and when you play Scrabble. And of course, this intuitively makes some sense to us because we're all kind of familiar with the relative frequency of letters. So we all read, we all look at written sort of text sort of frequently. So our brains have pretty much learnt some sort of patterns that are associated with the relative frequency of letters. So it's no surprise that the letter Z has 10 points associated with it because we all know that we don't see many words with sort of a Z in it. So our brains are kind of attuned to the relative frequency. We're kind of attuned to the expected frequency that we would see some of these sort of letters. And of course, we're also relatively well tuned to the structure of the letters because letters don't just appear independently, they appear in words and they follow certain patterns and certain rules in the way in which they appear with sort of words. So if I now show you sort of a plot where we plot the joint probability of letters appearing together, we can look at the joint probability of the first sort of character and the sort of second character appearing together. And intuitively, all of you will know that the Q is not frequently followed by any other letter than the Y. So we are familiar with that structure. We infer, we make these inferences that if I see a Q, then the next letter is going to be a U. And that underpins a lot of our reading skill, this ability to make inferences, the ability to learn the rules, the patterns that sit beneath the way language is structured. So if I make that sort of clearer, what we can do is plot the conditional probabilities. So on the left-hand side there, you can see the probability that this probability of the sort of second sort of character given the first sort of character. So now if we just have a look at that conditional probability, of course, it's far more likely that we're going to get a U followed by a Q. We just know this. Our brains are attuned to this because that's the structure of language. So the point is that humans are really, really good at making inferences. We're really, really good at getting tuned in to the structures, to the sort of patterns within the information to which we're exposed. We're tuned in to the state of the universe in all its various forms. Okay, so I promised that I was going to teach you 3 games. So we talked a little bit about Scrabble. I now want to just talk a little bit about Wordle. which is a great game, free to play. So let me just tell you a little bit about Wordle. So Wordle is a game where you get 6 shots to guess a 5-letter word. So what you do is you type letters into a box, the top box on the screen there, and if you manage to type the right letter and you get it in the right place, then the next time round, Wordle will change that to green, and it tells you got the right letter and you got it in the right place. Alternatively, you might guess the right letter but get it in the wrong place. And what Wordle will then do is change that to yellow. So what happens is the game gives you some information, it gives you some feedback on how you're doing, which helps you refine your guesses. So if we just sort of think about sort of a Wordle from an information theory perspective, we can kind of imagine how that sort of a game came to sort of a pass. So in the first sort of stage, you can kind of imagine it's like, well, let's just get people guessing random letters. And let's not give them any feedback. So let's just have the 26 letters within the English language. And what they've got to do is guess which letters we have within the sort of a grid. And we'll give them 6 guesses per day and see if they can do it. Now, that's actually a very, very difficult sort of task. And in fact, when I sort of calculated how long it would take you to solve that task, given you have 1 shot of this every day, it came out at around about 3.5 millennia. So really not much of a fun sort of a game. So you can kind of imagine that sort of game got sort of scrapped fairly early on, that this really doesn't work very well as an amusing activity. Although I think it's interesting to note that it gives you much better odds, or yeah, reasonably better odds than the National Lottery gives you. But for me, this isn't much of a fun game. What's a much better game is if we constrain the task somehow. So if you look at the way that Wordle has been developed, they don't just ask for random letters to be selected; they ask for words to be selected. And it turns out there's a relatively limited number of words within the English language. So the Scrabble dictionary reckons there's 8,996 5-letter words. But actually, if you boil that down to the common words that are frequently used within the English language, then that comes out at around about 5,757. And Wordle doesn't even use all of those 5,757. It actually uses a relatively small number of target words. It uses 2,315 target words, and it allows you to guess at 10,657 words. So if you put in a non-word into Wordle, it just won't accept it. You've got to put in one of its guess sort of words. And what you're trying to do is find one of the target words, which, as I say, are limited to 2,315. So this suddenly makes the game much more tractable. It means that you can actually solve the game in a reasonable time period. In fact, you can solve it every day. So if you're going to play Wordle and you want to solve the puzzle that the Wordle puzzle makers have set you, then I would really, really encourage you to use science to guide your first sort of word. Of course, I'm going to say that I'm biased. I'm a scientist. I believe that science is the most powerful tool that we have as humans to understand the sort of world and solve problems within that world. So I would really encourage you when you're playing Wordle to use science. And actually, we can use information theory to help us guide our first word choice. And it turns out that if you do the maths, if you kind of work out the Shannon entropy, that samey is one of the words that you're allowed to use within Wordle, and it actually reveals quite a lot of information. So that particular configuration of letters yields quite a lot of information. So if we type the word samey into Wordle, then Wordle will give us some information. We'll get some feedback on how close we are. So the grey letters are telling us that these letters don't appear in the word. And the green M is telling us that that's the right letter and it's in the right place. And the yellow is telling us there is an A in the word, but it's not in that position. So we've been given some information. And that means we now have a strategic choice. So we can either choose to use that information, that's strategy 1, or we can choose to ignore that information, strategy 2. Well, again, I'm biased. I'm a scientist. So I believe that the best strategy is to use science to guide the second word. So again, we can use information theory. We can use the information that's been provided. We can use our knowledge of words within the English language, and we can come up with a pretty good second guess. So here we go. Here's a reasonable scientific guess as to what the second word might be. So I've gone with the word nomad. So if I enter that word into Wordle, yet again, Wordle's going to give me some information. So I now know that the O and the M are in the right place, and I know there's definitely an A within the word, but I know it's not in that location. So again, I'm faced with a strategy. Do I use the information that's being provided to me? Do I use the information which is available, or do I ignore it? Well, again, I'm going to advocate whenever you play Wordle, use the information, use the scientific approach. So if we use the scientific approach, a pretty good third guess is the word comma. And if we now enter that into Wordle, lo and behold, we find that that is indeed the target word. So within 3 guesses, we've actually managed to solve the Wordle puzzle. So for me, this is a real testament to the power of science, to the utility of information theory in an everyday problem. So what we've seen is there's really 2 strategies that are faced in many of these situations. So strategy 1 is we use all of the existing information. So we can use everything that we already know about the words that appear in the English language. We can exploit information theory. We can use information that becomes available to us, and we can combine all of that information in a powerful manner. And in fact, we have powerful techniques, Bayesian sort of techniques that allow us to take information from many sources and bring them together to give us a good understanding. So that's a very powerful strategy that we can adopt. Or we can just ignore the information which is available to us. And I'm going to argue that that second strategy seems to be pretty close to what we're currently doing within the UK, where we have information on health systems, and we've got information on education systems, we've got information on social care systems, we've got information on policing systems. We've got lots and lots of information, but are we using it effectively to drive improvements in population health? Are we using it effectively to really improve our public services? I would argue not. And that's why we have Southport inquiries, which say if only information had been shared across these services, we could have averted this sort of a crisis. So I believe that we really need to start pushing for strategy 1 to be adopted by government. So what does this tell us about human intelligence? Well, it tells us that humans are pretty intelligent. We can process information, we can store information, and we can use that information to make inferences. Now, computers are also pretty good at some of that inference. And for quite a while, we've had artificial neural networks. So these are machine learning algorithms that use interconnected nodes organized in layers to process information and make inferences. And for quite a while, we've had what we call CNNs and what we call RNNs. And these are different neural networks that do different sort of tasks. So CNNs are very good at capturing spatial hierarchies. RNNs are designed to process sequences of sort of data. And they both do the job that they're supposed to do, and they do it reasonably sort of well. But whilst these are quite good for solving problems like Wordle, they're not very good at solving some of the other things that humans are very good at when humans make inferences on the basis of information. So what I want to do now is tell you about another game that I enjoy playing, and I'd encourage you to play if you're bored at work. And that's Minute Cryptic. So this is another game which is widely available on the web. And Minute Cryptic gives you a clue, a cryptical clue that you need to solve. So here, the clue is unlocking kindness, insight, and humility starts with reflection. And we can see that there are 5 letters. So we need to guess a word with 5 letters that solves that clue. Now, this is something that these neural networks are really bad at solving. And that's because several components need to be solved in order to unlock this clue. So let's just go through that clue. So that clue has what we call indicators within it. Here, the indicator is starts. So starts is telling us something about what we need to do to solve this clue. And the word start within a cryptic crossword often means that you should look at the first letters of the preceding word. Look at the letters of what we call the fodder. So if we look at the fodder, that's unlocking kindness, insight, and humility, and we end up with the letters U, K, I, A, and H. Well, that's akiaha. That doesn't make a sort of a word, but that's starting to unlock what we need to do in order to solve this puzzle. And we have another indicator within this clue, and that's the indicator of reflection. So we see the word starts, tells us to look at those first letters. We also see with reflections, that means that we should reflect. And one way of reflecting is reading sort of backwards. And if we read that backwards, lo and behold, we come up with the word. And you can see that the word itself captures the actual essence, the surface of the clue that we've been provided with. Unlocking kindness, insight, and humility starts with reflection. That is a form of Japanese poetry consisting of 3 unrhymed lines. And you can see that what we need to do within that minute cryptic clue, within a cryptic crossword, are various things in parallel. There's not just a simple inferential sort of a task, that we need to be looking at the whole puzzle, the whole clue, at the same time we're making inferences about some of its component elements. And this is the stuff that traditional neural networks find very, very sort of difficult. This is the stuff where humans massively outperform computers. But computers are getting much, much better at solving these type of tasks. They're still not there. But big strides have been made in the last 10 years. And those strides have been made by moving away from these individual approaches, CNNs and RNNs, and moving towards what are called transformers, which start combining these different approaches simultaneously. So the landmark sort of a paper was called Attention is All You Need. That first described the transformer architecture that makes inferences, but it does it holistically as well as locally, and it does it simultaneously. And this is the foundation of what we now call large language sort of models, of which there are many different flavors. And I'm sure the colleagues have come across Claude or ChatGPT or Copilot. And all of these different large language models are based on this fundamental architecture. And it's likely this architecture is pretty suboptimal. And it's likely that there are probably much, much better architectures. But right now, it turns out that this architecture is very, very powerful. It's really, really useful at making inferences. And I'm guessing that most people in this sort of call have seen just how useful that can be in terms of generating text, because it taps in to the known structures, it taps into the known words within the English language, and it can then use that information, that sort of a structure, to make inferences and generate really powerful blocks of text using this transformer architecture. Can't quite solve minute cryptic clues yet, but that's definitely the direction it's heading in. And so the question is, can we start using this powerful technology to address the problem that we identified at the start of this talk, to really start accelerating evidence-based policy making? And this brings us nicely on to the subject of today's talk, which is Symphonia, which is a platform that's been generated to make the running of Delphi processes much more streamlined. That really leans into using large language models to do some of the heavy lifting, some of the administrative heavy lifting, which is otherwise associated with running big Delphi processes. So the Delphi process is all about bringing people together, experts together, getting them to independently input their viewpoints, synthesizing those viewpoints, identifying areas of agreement, identifying areas of disagreement, and then allowing the group to collectively iterate through all of the available information, all of the available evidence, until the group converge on a consensus position, which is the best reflection of the ground truth, the best reflection of the evidence that exists. And what that means is that suddenly that bottleneck problem that we identified at the beginning of this sort of a talk is overcome. Because unlike humans, large language models can do the parallelization. So they are able to take all of those individual inputs and synthesize them in a really efficient way. And when we do a formal analysis of the savings, they're considerable. And notably, those savings increase exponentially as we pull in more and more sort of other people. So what this means is that we can suddenly run Delphi sort of processes in a much more efficient, much faster sort of way, but also in a way that gives us greater diversity. We can bring in more experts from a wider sort of a range of areas. Now, we then need to make sure that the large language sort of a model preserves any disagreements and preserves sort of uncertainty. So what we've got to make sure is that the large language model doesn't just compress everything into a single unified sort of viewpoint. That's the danger, potential sort of danger of the large language sort of a model. So what we need to do is pull together all these different sort of viewpoints, but retain the basic structure. So what we really want to do is synthesize everything, but preserve the disparity. And what we've been working on over the last few months are techniques that allow us to preserve that disparity without getting that catastrophic collapse, that really allows us to get a very, very accurate, overarching view of all of those different viewpoints that allows the group to converge on a consensus opinion. And what's really important within this process is that humans are kept in the loop. The point is the large language models are pulling together all of the information, synthesizing it, doing all the administration, but it's humans who ultimately look at that outcome and make decisions as to whether that outcome properly reflects their opinions. It's humans that can bring different sort of viewpoints and say, well, I don't quite agree with that. So the human in the loop is absolutely critical. But so is the large language model in the loop, because it's the large language model that suddenly makes this a realistic proposition, that at pace, you can pull together a whole bunch of expert opinions and come up with the evidence that policymakers require. Bearing in mind that policymakers are often working under really tight deadlines, that they may be responding to an emergency where they really need to make a decision in a very, very short time period, and they want to base that decision on the best possible evidence. But how do they pull that evidence together at pace? And we feel Symphonia, this large language model platform, starts giving us a route to that evidence-based policy making, whilst bypassing all the bottlenecks that are associated with having humans entirely responsible for the process. Now, there's different ways that we can synthesize the information from these individual inputs. So one way is we can just use a single large language model. So we might just take ChatGPT and rely on ChatGPT. Now that's low cost, it's computationally very efficient, but also potentially biases the synthesis. If we just rely on one large language model, what we found is that we can get a loss of some of that disparity of opinion. There are other approaches, diffusion approaches, which give a really, really good outcome, but they're computationally very, very expensive and they take a long time. So what we have found is that a hybrid approach is the best approach to bring together the opinions at sort of a pace, preserve all of the disagreements that we want to keep within the Delphi sort of a process, but be computationally efficient. And this approach is a large language model sort of council, where we run a number of different large language sort of models. So Claude and ChatGPT and so on and so forth. And where each one of the large language models marks the other large language model's homework. And this is quite an efficient way of synthesizing the information. And what we're finding is that it gives us a really good artifact, that gives us an artifact which captures all of those different opinions, but in a way that preserves any differences of opinion, whilst allowing you to see where the real commonality, where there's that consensus that will allow policymakers to proceed with confidence. So this is the underpinning science that sits behind the platform. And the platform will allow you to use just a single large language model if you just want a quick and dirty outcome. It'll allow you to use diffusion techniques if you want a computation expensive but really, really rigorous synthesis, or it allows you to select the large language model sort of at a council, or it allows you to design your own approach. But our preferred approach right now is to use the Large Language Model Council. So what do you do if you want to play with Symphonia? Well, go on to the Yorkshire and Humber Applied Research Collaboration website, where you will find the Symphonia site. I think Divine's put it into the sort of a chat, so you find it easily. And if you go onto the site, you will be able to click on the platform, and it will take you to the login page. And on the login page, you can create an account. And that account will then allow you to start harnessing the power of the Symphonia platform so you can start running Delphi processes at sort of a pace. And the software we think is very user friendly. It allows you to set up a Delphi process in a very straightforward sort of a way. You have toggle on and off sort of buttons. You can ask sort of people to adopt a position. So you can set a question. You can ask them for their answer that sort of question. You can ask them to give evidence that backs up their answer. You can ask them to provide counter arguments. You can ask them to judge their confidence. So there's sliders which people can drag along to sort of say how confident they are in their description. And you can create your own questionnaire, your own sort of Delphi sort of a process. The platform will generate a code. You can then share that code with your experts who can then start the Delphi process. And then behind the scenes, the platform will do the large language model council. It will produce the synthesis. We can go back out to your different participants while you iterate until they're really, really confident that the artifact that's been produced by the platform best represents the group's position on a particular topic. Again, I can't emphasize enough, humans are completely in the loop. The final artifact should entirely be signed off by humans. All the platform is doing is it's just decreasing the administration involved in getting everybody to input independently in the first place, so they're not biasing each other's opinions, and then just really harnessing all of the large language model's capability of pulling that all together in a very, very short period of time so people can get onto the next sort of stage without relying on some slow, inefficient, almost certainly biased human to deal with those bottlenecks. And this is exactly the process that we're following right now as we seek to answer the question that I said we've been sort of set at the outset of this sort of talk, which is effectively how can the UK use its data assets more effectively in order to improve outcomes for children and young people. So we've made a number of recommendations to the government, and we're now asking our expert community to give us their feedback on those recommendations to make sure that when we hand our report back to government, we know it truly reflects the consensus opinion across our whole community. So this is the process that we're going through right now. And I think it's fair to say, a little bit of a sneak sort of preview, I think it's fair to say that what we're really finding is that the consensus position is we've got to make better use of the data assets that we possess within the UK. And we've got to look at the model that is connected West Yorkshire, where within Bradford, the approach of Bourne and Bradford has successfully sort of shown how you can connect health and education, social care and policing sort of data. And in line with all the conclusions that we've been reaching throughout this sort of a talk, using all of the available information and using it effectively is genuinely transformative. We can suddenly make inferences about how we can improve all of our public sort of our services. So we're in the process of coming to the end of this process, really testing the Symphonia sort of platform. But I think it's sort of fair to say our interim results sort of suggest strongly that we're going to be recommending better use of connected data sets using the connected West Yorkshire model. And I think we're going to be recommending Symphonia or variations thereof as a real way forward as we start to use large language models to accelerate evidence-based policy making. And that's where I'll end so that we can have some time for questions. So I will stop sharing and then Divine, I'll hand over to you if people have got any questions.
Thank you so much, Mark. It's really interesting. If you got any questions, please put it in the chat and we'll answer it. Or if you want to raise your hand or want to talk as well, that will be open as well. They're all like big clapping. Thank you.
That's Chris Brown and Lydia. I've paid them to put claps in. So.
We've got a question from Lorna. Are we allowed to use it for our own Delphi processes.
Great. That's exactly what it's for. It's all open source. In Yorkshire and Humber Arc, we're here to help. That's our job, to try and drive improvements in population health. We have a data science AI and sorry, data analytics AI and visualization theme within the Arc, and our job is to help everybody on this call and beyond to do great work. So anybody who's doing anything to improve population health, we would love to use the platform. The platform's kind of ready to go, so hopefully colleagues will find it fairly easy to use. But it's also just open source, so it's very easy just to fork off the software so you can develop yourself. We're trying to develop a sort of vibe coding element to the platform so that colleagues who are less familiar with coding can just actually put written words in, sort of saying, "Oh, can you do it in pink rather than blue?" And the vibe coding modules will ensure that those verbal instructions, if you like, are translated into the code changes that you want. So hopefully it's just a really powerful platform, which is, as I say, freely available to everybody. It's all open sort of resource. It's just a scientific contribution, and like any other scientific contribution, we do it for societal benefit and no other reason.
She got follow-up questions like, how do you get around needing to enter a valid join code?
So say that again, Divine.
How do you get around needing to enter a valid join code?
Okay, uh, so there's two ways that you need to log on. So you either log on as a user where you're being asked to. There's two uses. So one is where we send it out and you sort of log on and you're asked to complete a given questionnaire. So that's the process that we're doing right now. Or you log on as a test user and then you're creating your own one. So anybody who wants to actually use the platform for their own Delphis, if you just reach out to us, contact us, then we will set you up as administrator so you can then create your own sort of a Delphi process. But I'm guessing what's happening right now is people are logging on as if
Clicking
they're a
it in.
user, and so therefore they need a code in order to participate in one of our ongoing Delphis.
Okay, lovely. And we've got a question as well. Just logged on but can't see how to create a new question,
Yeah,
which is like
that's
no
because we need
contact.
to log you on as administrators rather than users. So just reach out to us and we'll get all that set up for you.
Lovely. Thank you.
And I can see Kate would like to be a Delphi person. Kate,
Yeah.
consider yourself a Delphi person. We will get you set up.
Any more questions for everyone? Just a thank you. Any more questions?
Good. Well, as we said, Divine, it's all there on the website. You can read a little bit more about it on the website. Anybody who'd like to use this, please join our merry gang. We think this is really powerful. So I think particularly sort of Megan Wood, myself, a number of sort of colleagues, we hurt as we pull together those Child North reports, because at some level there's just a lot of heavy lifting in terms of just the administrative, boring sort of bits. The more that we can use these powerful technologies to decrease that pain, the more we can actually focus on the good sort of science, the more we can actually use our human brains to make sure that what's being produced is of the highest sort of quality. So we really believe in this approach. It's obviously just first sort of steps, but we really feel as a community we can get behind this. It could revolutionize how our policy making happens. So it's not just some Secretary of State sat in a dark room with a wet tea towel around their head. It's actually properly based on all of the evidence that our academic community is producing. So we really can start sort of seeing evidence finding its way into policy.
We've got a hand, Jasper.
Hi, yeah. Thanks, Mark. Excellent project, very timely and inspiring. I suppose I wondered, the commercially trained models, of course, they are fine-tuned to avoid certain topics, maybe, both probably in the engineered client as well as, or in the API, as well as maybe fine-tuned into the model even. And these topics may be relevant to the topic at hand for the experts, right? Like I'm thinking about the care setting, for example, and the abuse and these kind of things that are relevant for this domain. What's your thoughts on that? And do you think there's ways around that?
Well, so one way is, I guess as a community, we start, moving away from all the commercially available sort of models and start sort of tuning our own sort of models is one thing I think we could and should be doing. I'm very worried at the extent to which we're letting tech bros have control over every aspect of our life. But also I think it's just the keeping the human in the loop. So again, it may be that there are more or less elements that we need to go in and I don't know, fine tune as sort of our humans to get the sort of the synthesis saying exactly what we want it to sort of say. But even those situations, just a lot of the sort of tedious, just pulling together information into one sort of a place, identifying where there are sort of commonalities is still, I think, massively advantageous. So I think there's probably a big continuum. Sometimes it will be bang on the money, do a great sort of job. You'll be 98% there just from the large language model council. In other times, actually, we are going to have to go in and do some of the sort of manual sort of corrections. But as I say, as the models themselves get better, as we start developing our own open source sort of models, hopefully these are things that we can get around. This is only the beginning of the journey, but I am optimistic about where this journey might sort of take us. And I say, hopefully it's about using AI for good rather than for making Elon Musk even richer. I just saw Rebecca's sort of question: how do we get the bias to each professional? I mean, that's that's science, isn't it? All of us bring sort of a bias. I think the best correction was peer review. It's like all of us sort of challenging each other in a very constructive sort of way. And again, I think this is what this process allows us to do. I mean, what we're really getting at is the whole peer review sort of process. Ultimately, rely on experts to sort of say yes, the evidence reaches the threshold, and iterate through that sort of a process. I think this just makes that whole process explicit.
Mark, I will be able to share the slides to all the attendees if that's okay.
Of course.
I'll send an email around to everyone with the link of the recording and also with the slides.
Brilliant. Good. Any other questions for us, Divine?
Say thank you. I think that's it.
That's good. Well, it's been really lovely to chat to everybody. As I say, we're very excited about the potential for this platform. We're looking forward to working with everybody using this approach and all of the other data analytics, AI and visualization approaches as we all look to make sure that everybody in the UK is as healthy as they can possibly be. So thanks so much, Divine. Thanks so much to everybody.
Thank you so much, everyone. Thank you, Mark. Thank
Thanks
you.
then. Thanks, Ray. Bye-bye. Bye-bye.